Hey kids, time for another day of improper integrals. Our big idea for today is how do I avoid integrating when I'm doing an improper integral? So, in other words, what if I just want to know whether my improper integral converges or diverges? And remember, we talked about converges meaning a sum that is, right, a sum that you keep adding such infinitely small amounts that your sum is confined to the house, versus a divergent series where the sum just keeps accumulating. Even if you're accumulating small values and adding them, they're still too big to be contained in the house. If I just want to know this fact, versus knowing, hey, this improper integral converges to 2. This improper integral converges to pi. This improper integral converges to a half. If I don't need to know the number that I converge to, maybe I just avoid integrating whatsoever. That's nice. So in tonight's homework, you're not going to integrate at all. All you're going to do is use these 3 pretty famous improper integrals as a basis for comparison. So I'm going to highlight the improperness first, and then highlight the piece of the integral that matters for our improperness. So number 1 is a p-series. You may recognize that from your pre-cal days. The integrand itself is a p-series where 1 is in the numerator and x to a power is in the denominator. If you have an improper integral going to infinity, that function approaches its horizontal asymptote as you go off to infinity. So you're going to start at some number b, approach the horizontal asymptote, so you are bounded on the left end, and you are collecting area under here, summing all those rectangles to an unbounded piece, right? Because you never do hit the 0. That sum will converge, collapse, stay in the house as long as that power is greater than 1. And will diverge if that power is 1 or less than 1. Okay, that's nice to know. I don't notice there's no value to which it converges. I didn't ask you that. I just want to know if you converge or diverge. Now I can prove this because I can actually evaluate this improper integral and I can give you a number. That's great, but I don't have to if I just want to know whether you converge or diverge, whether the given improper integral converges or diverges. So that was the case where you are going off to infinity, and if your power is greater than 1, it just means that the function falls towards that horizontal asymptote fast enough to create convergence. If the power is 1 or greater than 1, it just doesn't fall. These pieces here are too big. Even though you're going to add smaller and smaller numbers, these are too big in here to allow convergence to happen. This one is super famous. If you remember nothing else, remember this one. Number 2, not as famous, because most of these improper integrals series, when you actually go to apply them, are going off to infinity. But if instead you are going to the vertical asymptote, if you're going to the vertical asymptote, that means your graph looks like this. I mean, it's still the same freaking graph. One white. Oh no, it's red. But this time I want to talk about bounding it on the right side and unbounded at the vertical asymptote. So that improper integral, right? It's improper because you have the vertical asymptote at one of the limits of integration, flips. And it converges if you have p less than 1. And diverges otherwise. Notice x to the first is in the divergent category no matter what. Okay. Our last one is another famous function, and hopefully it makes sense to you. That both of these have the horizontal asymptote at 0, but when the coefficient up here in exponential land, when a is positive, so e to the x, e to the 1x, right? E to the 7/2 x. You have a slide swoosh. So as you're going off, this is another improper integral going to infinity, right? You're starting at some number b, and you're going to infinity, so you're bounded on the left, but not. Hopefully you can see that there's no containment here, right? This sum, right? You're not only is the function going to infinity, so is the sum, right, of all those rectangles. So converges if a is less than 0. This was a was positive, but if a is negative, you've got e to the negative x, or e to the negative 7/2 x. Doesn't matter the magnitude of that number, just matters whether it's positive or negative. This case, you have the swoosh slide. Whoops, that's terrible. I didn't draw close enough, did I? So as you go off to infinity, as long as your coefficient up here is negative, you will approach this graph, no matter the magnitude of the dilation factor up there in exponential land, as long as it's negative, will collapse down to the horizontal asymptote fast enough to create convergence. Again, I can prove this because I can evaluate any of these integrals. You can integrate e to the stuff. You can integrate 1 over x to the stuff. You can integrate 1 over x to the stuff. These are just so famous, it's just nice to know that they do automatically converge or diverge just looking at the power on 1 over x to the p and looking at the coefficient on up there in exponential land on e to the ax. Now, the reason these are so important for today's lesson, we're going to be using these three, and again, primarily number 1, to compare to a function or an improper integral whose integration I can't do, or it would be really difficult to do. So remember, to evaluate an improper integral, I actually have to evaluate an integral, right? We get rid of the improperness, we put a limit up there, we do integration work, the fundamental, right? The second part of the fundamental theorem, or the integral evaluation theorem, however you want to call it, we actually do integration. What if I can't do the integration? What if it's, right? I told you there are some functions that have no algebraic representation for its integral, or one that I either don't know the techniques yet or just freaking too hard. And it's not worth my time. Look at that one, right? That is not one, I can't do U substitution on that. It is not inverse tangent. I could do integration by partial fractions because I can factor, what is that? That's a sum of perfect odd powers, x to the fifth, 1 to the fifth. I don't think so, right? No, even if I can, I don't want to. So I just want to know if it converges or diverges. Okay, without doing the integral, Uh-oh, I'm still videoing. Or did I stop it? No, I'm still going. Sorry, kids. Okay. What if I just need to know, do you converge or diverge? I don't need to know converge to 2 or divert, right? I just want to know converge, period. So look very closely at that integrand. Does it look familiar? Not exactly, but look at that list that I just asked you to make, 1, 2, and 3. I'm going to compare this improper integral to one I know, a convenient p-series. There's lots and lots of p-series. The one I choose is 1 over x to the 5th. That is a p-series. Of all the p-series in all the world, I chose 1 over x to the 5th. Do you see why? That's what I mean by convenient. Think convenient means cousin. Cousin means you're not a twin. You're not exactly, you might not even be siblings, but you have some similarities. You behave similarly. So let's pretend this is the function I know. I know, remember me from my list, here's 1 over x to the 5th. 1 over x to the 5th is a known p-series that converges because that power is greater than 1. So here's my converge notation. Okay, I collapse fast enough to the horizontal asymptote to create a convergent sum of all those rectangles. Do I have cousins? Does 1 over x to the 5th plus 1 behave close enough to my original function? It does. It only differs by this plus 1. So yes, I'm cousins. But notice how I drew the blue function. This is a really important question. Which function has bigger y values? And what I mean by who is bigger, I mean compare the range values at each version value of x. So if that's confusing to you, just use a number. 1 over 2 to the 5th is 1 over 32, right? How about 1 over 2 to the 5th plus 1? That would be 1 over 33. Who's bigger, 1 over 32 or 1 over 33? How can I tell? My number sense, that's how. So I claim that the convenient cousin p-series that I know something about, I know its graph, I drew the convergent squiggles, then I figured out that the function I don't know lies under it. Do you see why that's important? If 1 over x to the 5th is one I know converges, and the one I don't know, but that is a cousin because it behaves similarly, lies under it, it's kind of sort of like 1 over x to the 5th captures it. If 1 over x to the 5th keeps us, right, its sum is will stay in the house, so will a function that behaves almost exactly like it, but is under it. Notice I didn't do any calculus. That's the direct comparison test. The direct comparison test for improper integral states, if you know that a function converges, and you know you have a similar behaving function, but that similar behaving function lies under it. So look at this weird graph I drew. I don't really care what happens at the beginning. I really only care what happens at the end. I'm going to infinity. Then the function that is similar, that you don't know what it does, but lies under the function you know converges, must converge as well. as long as you're under. Conversely, if you know a function diverges, so let's pretend I have a function 1 over x. Looks like that. I know it diverges. So I'm going to draw busting out the house, right? If it diverges, as long as the function you don't know lies above it but behaves similar to it, that unknown improper integral will diverge as well. Important. You have to know some functions. I gave you that list though, 1, 2, and 3. 1 and 2, both p-series, one about going to infinity, one about going to the vertical asymptote, and then the third one was your e to the. Those are your 3 basics. Then all you have to verify is whether you have, oh gosh darn it, cousins, right? Which means they behave similar. And then you have to show that you know the position, under or over. So here's what you need to write down. Notice there's not going to be any calculus. No integration. Since there's no integration, you're going to have to write more because you're not writing limits, you're not evaluating an integral. So here's how you state and justify using a comparison test. Since a function that's a p-series and I have the improper integral going to infinity from my list converges, and further, here's how I know it converges, right? Don't just tell me that you remember it. That's great that you remember it from your list. Tell me what you know about it. So this is your known. What do you know about it? Make sure they're pretty similar. Then talk to me about position. Since I converge, since I know the series I chose, or the improper integral I chose converges, it has to be on top of the unknown of the cousin. I put this statement here. You don't have to put that. You don't have to put that. But sometimes there's an issue with this number down here and you're not sure what's going on, that, oh, you know what, at the very beginning, my known function isn't on top, but at least it's on top at, after 10 or something. When you're going to infinity, who cares? I don't really care if it's on top the whole time. Just needs to be above your cousin for, as you go off to infinity. So that's the only reason I put that down. So talk to me, right? You talk to me about which one is the bigger function. And since, again, I'm converging, I need the bigger one to be on top. Then it is true that the unknown cousin also converges, and then name the test. And you can just say DCT if you like. Okay, so 1, who did you pick? 2, what do you know about who you picked? 3, make sure they behave similarly. They look similar enough. Position, that's 3. And then 4, your statement of converging or diverging. And then 5, what test you used. Okay. So no integration. Awesome. But I have a function that I did not want to integrate, right? This improper integral I did not want to integrate. No, I know it converges by the direct comparison test. Be careful, again, I could not say what number our improper integral. I could this one because I can integrate this one. This one is my known. I could integrate it and get a number. Now, it's true that actually any improper integral, all the improper integrals you did last night, if you have another function that looks very close to the one you did in the previous homework, you can use it as it's available to use for a comparison test. Once you know it's been, it either converges or diverges, bam, it goes in your bag. It's just that you're not going to remember all those, but you're going to remember the P series and the E to the series, or improper integrals. I could evaluate for a number, but I couldn't this one. Could not say what number this improper integral converged to, just that it did converge. That's all I can say, and I can say it by the direct comparison test. Now, I skipped example 2 is we'll do in our live session, but I'm going to go on to example 3. Now, in reality, this is an improper integral I could do myself, right? It is just a u substitution with an ln situation. But I'm going to pretend I don't know how to integrate it, or I just don't want to integrate it. I'm going to do a direct comparison test. Who do you think I'm going to choose? Yep. Are they cousins? Pretty close, right? Pretty close. And what do you know about your choice? So here's what I know. Here's my known choice. Choose your known. Tell me what you know about your choice. It's a P series. P is equal to 1. Therefore, it diverges. They look enough alike. Just like before, right? My denominator is bigger, so my overall ratio will be smaller. So 1 over x lies on top. So I did 1, 2, 3 verified cousins and position. Here is my known 1 over x. I know it diverges, so the sum busts out the house. Oh. Do you see what's the matter here? My purple function is bigger. They are cousins, check, but it's the wrong position. The wrong position for my conclusion. Do you see that? Since 1 over x diverges, the person I'm comparing it to, the improper integral I'm comparing it to, has to be on top for any conclusion to be possible with the direct comparison test. The position is not right. No conclusion is possible. Dagger. Dagger. Fortunately, there's another test to get me out of that situation. The limit comparison test is another way to avoid calculus and avoid integration. But when I'm like, I gotta without a calculator, I have to picture which one's bigger. Should that function, the bigger function, the one I want to know? Is it convergent, divergent? Who's on top? Who's on bottom? Oh, so annoying. If you can show that both of your known and unknown functions as you integrands, as you go off to infinity, behave the same way using a limit, then you can conclude that they both behave the same way for either staying in the house or busting out the house. But of course, you still have to have a known improper integral, either from your list or one that you've done before in a previous homework. And then the limit will show that they are cousins or not by doing the limit. Let me show you what I mean. So we're going to go back to this example, 1 over x plus 1, that we pretend we don't know how to integrate. We tried the direct comparison test, and the position was wrong, right? We had a dagger. For the limit comparison test, I do a limit, but this is not the improper integral limit. I'm always going to take the limit as you go off to infinity. And notice that I've got my known integrand over my unknown integrand. And it doesn't matter which ratio, right, you make, right? It's just a ratio. I'm doing a limit of a ratio, so I don't care. You could put 1 over x plus 1 on the top and 1 over x on the bottom. Does not matter. But for this one, step 1 is the same. Choose your known. 1, 2, or 3. The limit is going to show that they're cousins. I promise. I'll show you how. I did that limit. I plugged in infinity. 1 over infinity is 0. 1 over infinity plus 1 is 0. Uh-oh, what's that ratio? Zero over 0, or if I cleared the fractions, I forgot that I did that, right? I just cleared the fractions, right? I did 1 divided by 1 over x plus 1 is the same as 1 over x times x plus 1 over 1, which gives me infinity over infinity. Regardless, 0 over 0 or infinity over infinity, what happens? Oh, Guillaume, it's time for Guillaume. So happy to see you, Guillaume. Yep, L'Hopital. So take the derivative of the numerator, the derivative of the denominator, and you got 1. This is not the value of the improper integral. This is the limit as you go to infinity of the ratio of your known to your unknown. You have a cousin because the limit is a number and not infinity. Okay? There's a proof behind that, but that's why. Speaking of proofs, side note, do you remember being in Algebra 2 and Pre-Cal and doing end behavior? And we told you that if you had a ratio of, right, 2 polynomials, right, which was a rational function, and I wanted to know the end behavior, you looked at the leading coefficients, right? And if your degree was the same, you looked at the ratio of the leading coefficients, and that was your horizontal asymptote. You were really doing limits. You were really doing L'Hopital's. L'Hopital is the proof of that shortcut, right? It's kind of cool. Anyway, little side note. Truth be told, if you set up this ratio and then just drop to 1 without doing L'Hopital, I'm totally fine with that. Right? You can use your shortcuts. But you do need to do each one of these things, right? I do need to see the limit set up. So what do we write down for these? Since I got a number, these similar behaving functions go toward infinity at the same rate. Remember, your derivative is a rate of change. They go at the same rate. Therefore, they both will converge or diverge, depending upon what your known does. So what you write down, since what you know diverges. Tell me how you know it diverges. Then set up the limit. Tell me what the limit is equal to. Again, I don't really need to see a lot of limit work here. If you already know what this is, you can just tell me. You can just write it down. Or if you have to do limit work, well, then do limit work. Because you got a number that is not it's not an infinity and it's not 0, I know that they are cousins. Therefore, the unknown does the same thing as the known. I don't have to worry about which, since that diverges, the one I know has to be on top of it. I don't need that at all, right? Don't need to know position when you're doing the limit comparison test, but you do have to do a limit. Now, you do have to tell me the test that you're doing. I've done this by the limit comparison test. Okay, so 5 steps, just like before. Choose your known, tell me what you know about your known, set up the limit with the answer, give me your concluding statement and the limit that and the test that you used. This is just a formality. I can tell what test you used. Now, you do have to be careful with the limit comparison test. Sometimes you'll try to run the limit comparison test and the answer you get is an infinity here or a 0. That doesn't always mean I shouldn't say that. If you get a 0 or an infinity, the limit comparison test is inconclusive, but it doesn't mean that you have to bail on the limit comparison test. It may just mean you made a bad choice. Choose something else maybe and run the limit comparison test on it. So for example, sometimes you choose a cousin. It is a cousin, but it's a second cousin, right? It doesn't behave enough alike your given one to get that their rates of change as you go off to infinity is the same. So but just because you're inconclusive doesn't necessarily mean you have to bail on the LCT. Just go back and examine your choice and say, oh, is there, and usually it's an adjustment of the power, right? I think it was obvious this time to choose x to the first, but sometimes it's not as obvious. All right, we'll do more examples when we get together in our next live session.